Okay, welcome to EGR 456. In today's class, we are going to talk about mostly about project 4 and project 5. So I understand that despite of multiple efforts, some of you were not able to get correct answers. So I would like to outline what the solution looks like and how to solve problems whenever you have a project. So quickly, here are some recommendations. So in this class, we do not have homework or quizzes or exams or final. So we do not have any of these. Instead, we have projects. So these projects are expected to be involved. So expect some struggle as you work through the project. But I assure you, once you spend time working on the projects, you will have to do these projects in conjunction with reading the textbook. So just based on the lecture material that we discuss, if you jump on working on the project, most likely you will get stuck or you will go on to a wrong track. So whenever there is a project, before you start working out the project, please review slides, video lectures, and read the textbook, which is very important because many a times it may not be possible to explain all the concepts, or I may not spend more time on the things that I think you already know. So please spend time on reading the text. And as you are working on the project, you will expect that you will have to go back and forth between all this material, and that would enhance your understanding. So let me look at, if you have textbook, this would be a good opportunity to understand how to work out project 4. So I'm going to outline how would I work out. So working on project 4. So if you have the textbook, either hard copy or soft copy, I would strongly recommend that you open the textbook and follow what I'm doing. So first and foremost, I'm gonna kind of briefly go through what this project is looking for. And then I will outline the relevant section in the textbook that will give you hints to solve the problem. And then I will work through project 4. So project 4, you have section 5.1 that talks about trim and Lin mod. So we worked examples on trim and Lin mod, but I would expect you to work out those problems again. Work out problems again, just to make yourself familiar. 5.2, 5.3. So these parts, these are dependent on if you are going to use the files provided on the textbook website. You can follow this approach. And again, either approach is fine. Now, when you try to work out problem 5.4, step 1 is to see what is this project or problem asking? And I will read so that we understand the problem. And once we set up the problem, then we will step by step come up with a solution. So first we have to use a Matlab script to compute the trimmed state. So we need to find out trimmed states. That means the states at operating point. And it's a level flight. What do I mean by level flight? Level flight, which means the aircraft is not climbing, aircraft is steady. And whenever aircraft is steady, please understand aircraft is not a car. So you may observe that the aircraft will be pitching up, but still going in the straight line. It's absolutely possible depending upon what the conditions are. Now, the important parameters that are given here is VA, which is the airspeed, is equal to 10 meters per second. This is the airspeed. Now, we are going to assume, let's go through our next thing. Gamma is 0 degrees radian. This is nothing but the flight path angle, which is nothing but the orientation of the aircraft, sort of the orientation of the aircraft with respect to the projection of the ground path. So if you have an aircraft, there are two angles. One is the course angle, which is nothing but chi, and the other one is gamma. So value of gamma is given. Now we have to set the initial states to trim states. So trim states. Now there is a difference between the trim states and the derivatives of trim states. So trim states are nothing but all the excess. So remember the equations, we had 12 variables and we also had x dots. Those are again 12 variables. Now, and input controls. If your trim algorithm is correct, the MAV states will remain constant during the simulation and run the simulation for different values of gamma. So run the simulation for different values of gamma. So what we need to do is, we have to convince ourselves that this trimming is correct. Now, please understand, this problem is complex. So let me write this down. This problem is complex because there are 12 nonlinear equations. And depending upon the algorithm that you choose, depending upon the initial conditions that you choose, your answers or the solution would be different. So solution, this is important, solution depends on initial conditions, constraints, and the algorithm that you choose. Because this is typically done with a nonlinear optimization technique, and depending upon what algorithm you choose, you are gonna get the different answer. Now, with this information, what we need to do is, we need to go back to the basics and try to identify what exactly needs to be done. So let's go a step back. This is the Genesis block. And I emphasize that this is a very important set of equations. These are the 12 differential equations that govern the motion of the unmanned aerial vehicle. Now look at these equations. These equations are also given, and I want you to refer to the textbook at this point. So page 61 of text. So these equations are given in the page 61 of your textbook. What these equations tell us, these equations show us the derivative on the left hand side. So Pn dot, Pe dot, and then north, east, down. So PD dot is replaced by H dot. So this guy is actually PD dot. Then you have U dot, V dot, and W dot. So U is the velocity, forward velocity. V is the velocity around Y direction, and W is the velocity around Z direction. It might be instructive at this point just to outline what these variables mean. So what I'm going to do is I'm going to insert a new slide, and I'm going to kind of show you the aircraft. This is the aircraft. And let's assign north, east, and down coordinate systems for this guy. This is north, this is east, this is down. Now let's identify. So north is going to be X, east, actually let me use a different color. North is going to be X, this is X, this is Y, this is Z. So you have north, east, down. Now velocity in the north direction, this is U, this is V, and this is W. And again, this is everything is in the body coordinate frame. Now what we have is we have again the rotations, rotation about X, rotation about Y, and rotation about Z. So I have phi, which is roll. Then I have theta, which is pitch, and going down, what we have is yaw, that is psi. So this is roll, pitch, and this is yaw. Then in addition to that, we have the rates. So we have P, which is the body rate, radians per second. We have Q, and we have R. So we have P, we have Q, we have R. These are the body rates. Then we have U, we have V, we have W. These are the body velocities. And let's not forget, we have roll, we have pitch, and we have yaw. These are the attitude, or also the Euler angles. And last but not least, we have the position vectors Pn, Pe, and Pd. Pd is also called as height, because if you think about it, the position, and if this is your ground, then this is Pd, which is nothing but equal to h. Okay, any questions at this point? So these are the different parameters. And if you look at these equations on the Genesis block, they relate the derivatives with respect to the states. One thing that I want you to note is look at carefully, look at the equations for the body rate, body velocity, and Euler angles. And you will observe that Pn, Pe, and H do not appear in the equation. So what I want you to do is, I want you for a minute to look at the equation for P dot, equation for Q dot, equation for R dot, U dot, V dot, W dot, and then you have the equation for theta dot or rule theta dot psi dot. This is an important exercise, and I would like you to take a moment to take a look at these equations. The first observation is the PE, PD, and PN, they do not appear in this equation. Now, next observation is, you will observe that these equations are coupled. So if you notice these equations from all the way from here to here, these equations are coupled. And these are the key equations for trimming. So when we are going to trim, we are going to use these equations. Now, here is the classic objective. And again, let me emphasize, trimming means steady state. Trimming means steady state. In steady state, the derivatives are going to be zeros. So this is something you have to keep in mind. Derivatives are equal to 0. However, when you are operating with certain constraints, or you are having an aircraft to fly in a particular constraint or in a particular flight regime, you can relax some of those constraints. So now let's go step by step. Now what I want is, first thing, I want aircraft to fly in a level flight. So level flight. In level flight, what it means is I could have a non-zero U. So again, this is just for the level flight. So this could be non-zero. Then I would assume that V, and so U is non-zero, but U dot, the rate of change has to be 0. So I would state that my U dot is going to be 0. And at this point, what I want you to do is, as I discuss this trimming, I want you to take a look at section 5.3 from the textbook. This is absolutely important. Open section 5.3 from the textbook. And it is discussed later here when we talk about trim coordinates and trim conditions. But let me explain with respect to section 5.3. And I want you, everyone, to refer to textbook section 5.3. And I'm gonna highlight the comments that are made in section 5.3. And before you work out this project, I would expect, or I would suggest that you should actually go through this section 5.3 line by line and understand what we are trying to do here. So subset of states. So subset of states in equilibrium. Then what it's saying, that H has to be constant, minus PD is a constant. So H has to be a constant. Next thing is body frame velocities and Euler angles are constant, which means U has to be constant, V has to be constant. Please note, it does not specify what should be the value of that constant, but it is just saying that these should be constant. Next, Euler angles. So body velocities. The next statement is the Euler angles, which is roll, pitch, and yaw, they are all constants. They are constant, constant, constant. So Euler angles are constant. And this is coming from section 5.3, page 66. The next part is angular rates. P, Q, and R are constants. So you have constant, constant, and constant. Now, next thing is super important. Even though all these quantities are constant, since you are in trimming, the derivatives have to be zero. So what it means is U dot is zero, V dot is zero, W dot is zero, phi dot is zero, theta dot is zero, psi dot is zero, P dot is equal to zero, Q dot is equal to zero, R dot is equal to zero. So this is the constraint. Now what I want to do is, I want to take these constraints and go a step back. You will notice all these constraints are on the left-hand side of this equation. So this guy has to be zero. 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 Now the next question is, what is non-zero? So the non-zero values are given on the left-hand side. So H is equal to minus PD in level flight, it's constant. And then everything else is a constant value. The question is, what are these values? So these are body rates. And what are these values? To be honest with you, we really don't care what these values are. As long as all the derivatives are zero, whatever the values may be, we are okay with it. However, now let's look at the additional information that is provided to us. So the additional information is wind speed is equal to zero. Now, and again, I'm not saying something different. It is again given on page 66. So look at the next thing, VA is equal to VG, which is the airspeed is equal to the ground speed. So airspeed is equal to the ground speed because VG is equal to VA plus VW. Ground speed is equal to airspeed, and since this guy is zero, everything is zero. The next thing is chi is equal to the heading angle. So chi, which is the course angle, I will write this down here. This is the course angle, is equal to the heading or yaw. Now again, what we want to do is, why are the derivatives of H and psi not zero in the book? I'll get to that. Let me discuss. Let me go step by step, and then we will relax and we will see what are the essential constraints and what constraints can be relaxed. But just bear with me for a second. Let me develop this step by step. So now what I want to do is, so our objective, here is the objective, is I want the aircraft to travel at constant speed. So I want the aircraft to travel at constant speed. And this constant speed is VA. Now just think about it. Out of U, V, and W, if you have an aircraft that is going like this VA has to be equal to U. So which means my value of U, so this is the first piece of information that we know, that we want U is equal to VA. The next thing is, if it is climbing, now let me consider the climbing case. Climbing means going up. So if it is climbing, you have, this is the flight path angle gamma. This is the flight path angle gamma. And so it's going up by gamma. Now at this point, I want you to consider something like this. If this is the flight path angle, if this is the VA, then you are going to have two components of VA. You will have a VA sine gamma, and you will have VA cosine of gamma. So what this means is, if I want it to climb at a non-zero value of gamma, if it's climbing, it's going up. And then the last thing is, it's in the constant orbit. So we'll look at the orbit case a little bit later. So orbit means it's kind of going like this. This is R. So for the first case, let's assume the R is infinity, which means it is going in the level flight. And I'm going to say it's sort of traveling, the flight path angle is 0. So I'm going to assume the flight path angle gamma is equal to 0. Now I have to set up, yeah. Okay, I will say it minus U. So actually, I need to be clear. So if this is VA, that means U is like this. Because what's going to happen, you're going to have a pitot and static tube coming out of aircraft, and that would actually give you a measurement of VA. So it doesn't matter whether the air is stationary and the aircraft is moving, or aircraft is moving and the air is stationary. It doesn't matter from mathematics point of view. All right. And now we have inputs. The inputs are, you have a delta elevator, delta rudder, delta aileron, and you have delta T, which is thrust. And clearly, when you are looking at Zagi, it's going to be slightly different, but we will look at that in just a minute. Okay, so now what I'm going to do is, I'm going to set up the problem using these minimal constraints, and you will realize that it is good idea to solve the problem or start with as less constraints as possible. So we are going to start. So just a second here. So here is going to be my strategy. Start with minimum number of constraints. Get the solution. See if solution check if solution is acceptable. If yes, that's great. If not, see if solution can be improved. So what I'm going to do with this, and I want you to keep this in mind as I'm going to work through the problem. I'm going to show you how it can be done. And at the first iteration, I'm going to go to the Matlab file. So I'm going to, before I start Matlab, any questions at this point? Any questions at this point? And one thing I want to tell you, that you may or may not get a trim solution. So you may or may not get a trim solution because it's a nonlinear problem. And depending upon where you start, so you're trying to you have a very complicated equation, and where you start. If you start over here, this is the minima. If you start over here, this is the minima. So you have to kind of tweak your parameters and think about, like, you have 12 different equations, and then you are actually trying to solve those simultaneously. So now what I'm going to do is I'm going to go step by step, and I'm going to share my screen and I will show you Matlab. Okay, now you should be seeing my Matlab, and I will quickly show you what I have. I have all these UAV parameters. These parameters are corresponding to Zagi. Then what I'm going to do is I'm going to open the same file, which is derivatives 1 sim SLX. So this is the exact same file that we shared. And if you are with me, I would encourage you to take a look at this file. Let me open the chat window. Let me see where my chat window is. Okay, here is my chat window, and here is my Matlab file. And I just want to make sure that this is the exact same file that I shared in the last class. And this is the same file that we have been working with. So let me quickly look at derivatives 1. Can you see derivatives 1? Again, there are 12 states. Then you have 3 forces, 3 moments, all these equations. Then if you look at the Matlab function, if you look at the integrator, all the initial conditions are 0. You have this force moment 4 function, which actually gives you the values for different forces. And basically it might just be a good idea just to run this code to see if the baseline code is working. And it seems to me that the baseline code is working. There are no errors. Matlab doesn't say anything. Now, but as you notice that after some time, the aircraft kind of pitches down, and then it kind of becomes unstable. Now we would like to avoid this if possible. So what I'm going to do is, I'm going to go to apps, and then I'm going to open up all the apps. And in last class, I kind of gave you an idea of using the trim and the linearization at the same time. But let's try to do this in a slightly different fashion. I want you to see in control systems, there is something called as the steady state manager. So click on the steady state manager. So steady state manager can be used to find trimming point. Or if you want, you can use the linearization toolbox to find the trim point. Now here, you will go to trim specifications. So click on the trim specifications. And as soon as you click on the trim specifications, this block will open up. Now let me go through what this block is telling me. This trim function is acting on the derivatives 1 block. This trim function is acting on the derivatives 1 block, because this is the only block that has derivatives and integrator associated with it. Now let's look at what we have over here. Derivatives 1 sim integrator, state 1, state 2, state 3, state 4, state 5, all the way up to 12 states. These are the states of the differential equation. And you can actually find from here, these states, these 12 states correspond to these 12 states which are over here. So for an example, state 1 is Pn, state 2 is Pe, state 3 is Pd, state 4 is U, V, W, Phi, theta, psi, P, Q, R, and so on. Everyone with me so far? Then next thing is inputs. If you look at these inputs, these are channel 1, so derivatives 1 in 1, derivatives 2, ln2, derivatives ln3, derivatives ln4. These are the inputs to this block. These are all the inputs that are going. Then you have this output. Okay. This is my block. Just compare if your block is same as my block and you have defined inputs 1, 2, 3, 4 and outputs 1, 2, 3. So if your block is same, anyone else having that error? Okay. All right. Now moving on. Now what I want to do is I want you to observe something. Matlab to start with have actually added steady states. So basically Matlab by default has clicked all these to steady states. What this is telling me, that all the derivatives are 0. And no, Borna, just wait for a second. I need to discuss this in a little bit detail so that everyone understands. Bear with me. So what I want you to do is I want you to observe as soon as you open this, all the steady states are clicked. What this means that these values are 0. inputs are not mentioned and outputs are not mentioned. So at this point, what I want you to do is I want you to go to trim options. And when you go to trim options, there are multiple algorithms for optimization. There is gradient descent with elimination. There is gradient descent, simplex search, nonlinear least square, nonlinear least square with projection, and gradient descent with projection. Now, please understand, every algorithm has multiple options. So for an example, if you look at the gradient descent, you have active set, interior point, trust region, sequential quadratic programming. If you look at the gradients, just gradient descent, same options. If you do simplex search, you don't have any options. Nonlinear least square has 2 options. Nonlinear least square with projection has 2 options. And gradient descent with projection has 4 options. Please note, depending upon what algorithm you choose, depending upon what optimization method you use and what algorithm you choose, your answers are going to be different. Some optimization method and some algorithm may give you answer, other may not. That is just the way the optimization works. So what I'm going to do is just my first way, I go with sequential quadratic programming, which is called SQP. So gradient descent with elimination, and I use SQP. But again, you don't have to use SQP. You can start with active set. If active set fails, then you can try interior point, trust region, and then finally you can go to SQP. It's totally fine. It's nonlinear optimization, so some trial and error is expected. Now at this point, I have not added any other constraint except the derivatives are 0. And what I'm going to do is I'm going to run. Note, there is no condition on input, no condition on output, no specification on states. The only thing I'm suggesting here, or I'm implying, that the derivatives are 0. And then I will start trimming. Now see what happens. And if you want to see, it gave me an error. And that's absolutely fine, which means that optimization problem couldn't work. There are 2 choices at this point. You can go back, change the algorithm, and try to run and see if that algorithm works. And see if there is an issue with the algorithm or if there is an issue with the constraints. And then if you want to see the optimization iterations, if you double click on optimization iterations, it will go through all these different optimization iterations. And depending upon the computer that you have, it may take some time or it will continue to run for some time. Okay, all right. So again, I want you to note that it gave me the exact same error as the error that was earlier. What that means is most likely there is an issue with my constraints. Yeah, domain error is an issue with my constraint. Now, let me see out of these, what constraints are real and what constraints I have put additional. Clearly, there is no reason to have the constraint. And I want you to look at the notes which I discussed a minute ago. I don't want all the 12 derivatives to be 0. I just want first 9 derivatives to be 0. There is no need for this derivative to be 0. But I want the derivative on the state 4, derivative on the state 5, 6, all the way up to 9, up to 12 to be 0. And take a moment here and go back to the slide or the notes I wrote. U dot has to be 0, V dot has to be 0, W dot has to be 0, theta, psi, phi dot, all the dots should be 0, P dot, Q dot, R dot, they have to be 0. In other words, a step back These states from state 4 all the way to state 12, from state 4 all the way to state 12, they have to be 0. So now what I have done is, again, in my second try, what I have done is I have actually added state 4 to state 12 is equal to 0, and I'm going to click run and see what happens. Again, I got an error. Derivatives 1 SLX. So I got an error in this file. Now what I'm going to do is I'm going to add one more constraint. I'm going to say that my airspeed will VA, that has a constant value, and that is known. So I'm going to add 10 to the airspeed, because my airspeed, I want it to be constant. And honestly, other parameters at this point, I really don't care. So let me see if there is any issue with my Matlab. I may have to rerun, reopen and close and open Matlab. But let's see what happens now. It actually depends upon the algorithm you choose. All right. Now what I want you to do is, it gave me an answer. And I want you, let's look at this answer and see what this answer is telling me. This answer is telling me my state 1 is 0, state 2 is 0, state 3 is 0, which means my Pn is 0, Pe is 0, Pd is 0. My state 4, I want it to be 10, which is 10. Now, it is important to note, but the derivatives of the states, which is Pn dot, Pe dot, Pd dot, they are non-zero. That's okay. It doesn't matter. The derivatives here are non-zero. The most important thing here that, Zubir, just hold on a second. Let me finish this discussion and then I will answer your question. So I want you to focus something super important here. And this is what you should be actually checking for. From state 4 onwards, all the way to state 12, can you see that these derivatives are super duper small? I want you to note the derivatives of state 4 is 3 e to the minus 10. Derivatives of state 5 is 8 e to the minus 13. Derivative of state 6, 7, 8, 9, 10, 11, 12. All these states are very close to 0. Everyone understand that? Are you able to get the answers corresponding? Your answer may be slightly different, but the idea is all the derivatives of the 9 states, they should come out to be 0. And I'm going to wait here. I'm going to pause here for a second and see if there are any questions at this point. The state is not the integral of, okay. The state are the states in the Genesis equation, because if you look at the Genesis equation, we have 12 states and 12 state derivatives. These 12 states are Pn, Pe, Pd, Uv, W, Phi, theta, psi, PQR. And the steady state means the derivatives starting from U all the way to R, they have to be very small. Everybody understood this? Any questions at this point? I'm looking at the chat window. The next thing what I want to show you is, let's look at the inputs. And at this point, what we need to do is, we need to see if the actual values are reasonable or not. Now, please notice channel 1 is the elevator, then aileron, and then rudder. and channel -1 ln4 is the thrust. So as you can see, these values I did not specify, but these values were computed by the optimization routine. My outputs are here, and I want you to look at this output closely. Channel 1 output is nothing but my airspeed. Can you notice that my airspeed is fairly close to the forward velocity that I specified, which was 10. So initially, I set my state u is equal to 10, and I got output of 10.49. Then the derivative one, which is nothing but, as you can see, which comes from this output state. This is 1, this is 2, this is 3. 1, 1, 2, and 3. So 1 is about 10 VA. And if you want to notice what those are, go back here and observe VA, alpha, and beta are my outputs. My VA is about 10.4. My alpha is angle of attack, is about 0.3. And my beta, which is the side slip angle, is about 0. Yes, your output values will be different because again, it's an optimization depending upon what settings you have. Every time you run the optimization, you may get a different answer. But the key observation is your derivatives, they have to be 0, not the derivative for state 1, state 2, state 3. Clearly, they are not zeros. The UAV parameters are corresponding to Zagi. These are the UAV parameters for Zagi. Okay. Now the next step is we want to find out if this solution is reasonable and makes sense or not. So the next step is set input and outputs in specs 1. So specs 1, okay. My inputs, I did not apply any inputs. I did not apply any outputs. So what I'm trying to say is I'm starting with the least amount of constraints. I'm starting with the least amount of constraints and see what solution I get. And successively, I will add constraints and see if I get a reasonable solution. Okay, this is the report. In certain cases, you will get some parameters as red. And those means those parameters are outside the specifications. Next thing is you can set initial conditions. Everybody see this set initial condition button here? Click on set initial condition, and then you will see that exported report 1 to Matlab workspace, which is used to initialize derivatives 1_sim. So once you set the initial conditions, now let's see if this trimming solution that we obtained, does it make sense? Because it may so happen that this trimming solution may be good for a short time period. It may not be good for a long time period, because at the end we have these nonlinear equations and we have external system, external loops. So let's see. Now what I'm going to do is I'm going to click and then I'm going to observe what happens to this airframe. And this animation will be different than the initial animation that you ran. Now let's see what is happening with this initial animation. And let's see, and I want you to double click on this scope. Double click on the scope. And when you click on the scope, you will notice something interesting happening. And clearly you will see some values growing, some values not growing. So I would strongly recommend at this point to go to view and open the legend. And let's study this carefully. Let's study this carefully. So this is a solution of integrator 1. Integrator 1 is nothing but P, let me see, what is it? Pn. Then you have Pe. Then this, so this is Pn. This is Pd. This is H. So I really don't care about these three things because it doesn't matter. It needs to be in the level flight. So, but however, if you look at integrator 4, this is my forward speed of 10. It is dot on 10. Integrator 5, note it's almost 0. So you will notice integrator 5 is 0. And all other derivatives are staying 0. And some of you may ask me how it is, because please note, this aircraft is not tumbling, unlike the previous aircraft simulation where the aircraft started tumbling. This aircraft is not tumbling. That means this aircraft is in trim solution. Now, I'm going to take a minute here and pause and see if there are any questions. So this is your aircraft that is in trimmed condition. And you can notice it's not visible here, but the position is increasing. Position in north, east, down positions are increasing, but the aircraft is not tumbling like the previous case, which means the aircraft is in trimmed condition. Now, some of you may ask me, okay, but then why my aircraft is pitched up? To be honest with you, this is fine. The aircraft pitching up is okay. But then what can I do so that my aircraft is not pitched up? And let's look at that in the next case. But before I go further, any questions? Everybody understands the aircraft is in steady state now. It is in trimmed condition. When trimming, what is the point of the plane animating? Oh, just to see if the aircraft is tumbling or not tumbling, or aircraft is doing something crazy or non-crazy. And the animation is going to be different than the previous iteration. Did you export the states to get the integrator scope? No, I did not export anything. I just double click on the scope in the Simulink here. This is the scope. So this is the scope. I double click. I did not integrate anything. Okay, I can share that. I can actually. Okay, these are my Zagi parameters. But it should work very well for your Zagi parameters, because I did this for multiple students and it's working fine. Okay, the whole simulation ran and there was no issue. Okay, once again, I'm going to allow everyone to do the corrections. So if you want to modify your project 4 and submit updated file, that is totally fine. Okay, so now the next question is how this simulation can be modified for Zagi. Now there are two ways to do this, and I'm going to start with the easiest part. No, it won't be late. If you can turn in your corrections for project 4 by tomorrow. So corrections. Okay, now the next question is how do we modify this for Zagi? Now let's go back to the specs. Now what is the issue with Zagi? The issue with Zagi, and let's take a look at this for a minute. I want you to look at the output and see here what is happening. Now it is interesting to observe well, it is not possible, Jax. It's a perfect question, but what is correct? So what I'm trying to say here is, if your solution is not similar to the solution that I'm showing here, then I would like you to duplicate the results that what I'm showing and upload it so that you'll get full credit. Because it's not possible for the grader, unfortunately, to grade all 73 homework or projects in one day. So my suggestion is, you know what your solution looks like. If your solution, if you are not confident that your solution is correct or not, then I would encourage you to change it and make sure it is similar to what I'm showing here. Does it make sense? If you are not confident about your solution, I would recommend that you do correction. If you think your solution is correct and you are going to get full credit, then you don't have to. No, it should not tumble for the final. Did my aircraft here tumble? So your aircraft should not tumble as well. Now the question is, how do we modify this for Zagi? What is the key parameter with Zagi? The key parameter for Zagi is we do not have rudder. Now I want you to look at the solution that is being found here. First one is the elevator, second one is the aileron, and third one is the rudder. So first one is elevator. I'll answer your question, Ghazi, just a second. The first one is the elevator, second one is the aileron, third one is the rudder. Now, if you look at the trim value for the rudder is very close to 0. The trim value for the rudder is very, very close to 0, which means this trim solution would work for Zagi. This trim solution would work for Zagi because the rudder trim case. So basically what it means is rudder is not used at all. The rudder is not used at all. Now, if you really want to go back and if you want, again, these are all my conditions. If you really want to go back and add for Zagi, then I want you to go for spec 1. Yeah, that I will answer that question a little bit later. Just a second. Let me finish the Zagi discussion, Kazi. So if you want this simulation to run for Zagi plane, Zagi does not have rudder. So I would click known and I would have rudder at 0. That means rudder is always going to be 0. That means rudder is not available. And again, I will hit trim. and see what solution I get. Now, again, the important point to check is see if the derivatives all the way from here, from state 4 derivative, state 5 derivative, state 6 derivative, all the way to state 12 derivatives, all these 12 derivatives are close to 0 or not. And clearly they are close to 0. But what has changed? Please note, state 5 is no longer close to 0. State 6 is no longer close to 0. And state 5 and state 6 are nothing but, if you go back to here, state 5 is V, state 6 is W. They are no longer equal to 0. Let's look at phi theta psi, 7, 8, 9. 7 is close to 0. 8 is not 0. That's why you see the aircraft is pitching a little bit up. State 9 is not 0, which means the aircraft is now actually yawing. And that is how the Zagi is going to fly in the trimmed condition. Let's look at the input. Please note, rudder is saying at 0, which means it's not using rudder. But I want you to observe that the trim value for the elevator and the aileron and the thrust are now different. The channel value for the elevator has changed. Look at the output. You would notice that this value has changed, and now we have some side slip. This is absolutely expected. You will have some side slip in the Zagi unless you have the winglets. You are gonna get some side slip. And then what I will do now is I will set the initial conditions, and then I will go back. I set the initial conditions. So please note, exported report to Matlab, which is used to initialize derivative 1. And then I will run the simulation and see what happens. You will see the aircraft has yawed a little bit, because that is the trim state for Zagi, because of the way the system. And again, you click on the scope and you observe. You will observe the state 1, state 2, state 3, they are increasing, but other states are staying where they are, which means the aircraft is in trimmed condition. This is for Zagi. If you want to make this little bit complicated, to make it similar to Zagi, what you will have to do is you will have to add a mixing loop before the output. So before these inputs, so you have to mix the elevator and aileron as per the mixing matrix that is discussed in the textbook, and I discussed that in the last class. But now, as you can see, the aircraft, this is the Zagi configuration, is trimmed. Any questions here? And the aircraft that initially tumbled is no longer tumbling, which means everything is great. Aircraft is in steady state. Now let's try to investigate what happens essentially when you have a non-zero flight path angle. By the way, any questions here before I go to the next part? I'm going to pause here for a minute and see if there are any questions. Okay, there are no questions. So please note the simulation is running well. And yeah, I use the accelerator, but still it's not giving me any problems, which means it's working out good. Some of you may ask me, hey, my state 1, state 2, and state 3, they are changing. Clearly, the states PN, PE, and PD, they are changing. But why the aircraft doesn't seem to be going up? And I just want you to look at the scale. The scale here is from 5,000 to minus 5,000, 5,000 to 5,000, 5,000 to 5,000, and the change in the displacement is about 50, 40, and about maybe 5. So it's not possible for us to see the aircraft changing. But if you change the scale, if you reduce the scale to maybe 100 plus 100 minus 100, or maybe plus 500 minus 500, you will see the actually aircraft going up. Correct. To answer Zubir's question, your observation is correct. Delta E, delta A, delta ER, delta EL are not the inputs of the Simulink. So just so that I'm clear, this solution will work for Zagi. This is the correct solution because you are directly affecting the control inputs on the effect. So this is the effective elevation, effective elevator, effective aileron, no rudder, and thrust. Now please understand, effective elevator and effective rudder for Zagi is achieved by the combination of ailerons. So what you will have to do is, if you want to make it super realistic, you have to add a mixing matrix before. But your solution should not change. You don't really have to modify, as long as you set your rudder to 0. Yeah, this is nothing but effect. Okay, I'll go step back. What I want you to do is, I want you to look at the inputs. Can you see that okay, this is for report 1. So this is my effective elevator. This is my effective aileron. And I want you, and I'm going to give you the equation. Okay, can I answer this question during the office hours? Because this will take a little bit more time and some students may have other class. Okay, all right. So what I'm going to do is, and you are welcome to stay, but I want to take the last case, which is part of the project. So if you go to specs, the next case is you are adding the different values of elevation angle. Now, here is the key question. Where would you add this flight path angle? Now, flight path angle, which is called as gamma, where would gamma be? Basically, I want you to think about aircraft at a certain non-zero flight path. If the aircraft is in level flight, that flight path angle is nothing but the pitch angle. So I want you to go back to the derivative and see where that pitch angle is. So that pitch angle is this angle, 7. Oh, sorry, pitch angle is theta. My bad. Pitch angle is theta, which is state 8. This is phi, this is roll, this is pitch. So this is the pitch angle. This is the pitch angle. So which means my flight path angle, it's not state 9, Borna, it's state 8. This is the pitch angle. So what I need to do is, I'm going to go back to my states and I'm going to add my 15 degrees of flight path angle in the pitch. So I go to state 8. This is known. This is state 8. And please note, it has to be in radians. So 15 divided by 180 multiplied by pi. Now, one thing at this point is I want to take a moment back and see if this non-zero pitch angle, would it change the values of the derivative? And I want you to look at the notes that I talked about earlier. Will this change the values of the derivative? And here the answer to that question is yes, it will change the values, because now your airspeed, again, it depends upon how you want to state it, because your airspeed, if you are going to say airspeed is 10, then you are going to have the forward velocity, which is 10 multiplied by cosine of 15 divided by 180 multiplied by pi. This is going to be your forward velocity, and then your derivative, if you think about your height, that is going to change. But before we change that, let me run this for a second and see what happens. There is one more iteration that I would like to do, but before I do that, I want you to note that if you have a non-zero flight path angle, that simply means that you have a pitch angle. I'm not changing the inputs except the rudder is set to 0. Nothing in the output. And I say trim and see if it can find a trim solution. Now at this point, what I want you to do is see that I have got a trimmed solution, which means for and let's look at the value of state 8. State 8 is 0.26, which means it is at that flight path. And I want you to notice that the airspeed, because of, since the aircraft is actually lifted up, it's slightly less. But again, the key parameter is this. I want you to look at all these 9 derivatives. Are they close to 0? Yes, they are close to 0. So then let's look at the inputs. Is my rudder set to 0? Yes, my rudder is set to 0. Then let's look at my output. At this point, I know that my airspeed is not exactly 10, it's 10.6, but it's quite close. You can't expect your trimming to be just perfect on spot. And now what I will do is I'll set the initial conditions and then I will run. And now I will see what happens to my animation. And then I will see what happens to my plots. And you will notice that again, the aircraft stays in trim position, but please understand the height of the aircraft would change. And I tell you the reason why the height would change, because if you look at the inputs, if you look at the states, please note the derivative on state 3, even though the state 3 is starting at 0, the derivative on state 3 is non-zero, which means the height is going to increase, and which is quite natural, because as your aircraft is pitching up, you would expect the height to increase. All right, I'm gonna stop here, and if you have any questions, today's lecture will hopefully be uploaded by tonight. Yes, the corrections are due by tomorrow midnight. Okay, the project file already I gave extension on till Thursday. So I would encourage you to take a look at project 5, and I will give you hint for project 5. To get correct answers for project 5, you will have to really hit the book hard and study section. I'll tell you what section you will have to study. Just don't jump into working out the problem. You will have to study the section 5.5 line by line. Yeah, just a second. Let me stop the recording.